On the morning of September 13, 1985, at precisely 11:42 Pacific Time, Major Wilbert Douglas Pearson climbed the ladder into the cockpit of a modified F-15A Eagle fighter jet at Vandenberg Air Force Base in California, carrying beneath his aircraft a weapon that would rewrite the rules of orbital warfare. Soviet military strategists had spent 2 decades building a reconnaissance satellite network they believed operated beyond the reach of American retaliation, secure in the vacuum of space where no interceptor could climb and no missile could maneuver. The Kremlin's confidence rested on a simple calculation. Satellites traveling at 17,000 miles per hour in the cold darkness above the atmosphere were untouchable, invisible fortresses that could watch American missile silos, naval deployments, and bomber movements without fear of counterstrike. Within 90 minutes, that illusion would shatter when Major Pearson's F-15 launched a 3-stage kinetic interceptor into the thermosphere, obliterating a spinning solar observation satellite named Solwind P-78-1 at an altitude of 345 miles above the Pacific Ocean. The impact generated 285 fragments of orbital debris and sent an unmistakable message to Moscow. The United States had developed the capability to destroy satellites in orbit, and the Soviet Union's most critical intelligence assets were now vulnerable to precision elimination within minutes of conflict escalation. For Soviet air defense commanders who had dismissed American anti-satellite research as science fiction, the destruction of Solwind represented a strategic earthquake, forcing the USSR to confront a terrifying reality that reshaped Cold War deterrence and ignited a space arms race neither superpower could afford to lose. The roots of America's orbital kill capability stretched back to the early 1960s when U.S. intelligence agencies realized that Soviet reconnaissance satellites represented an existential threat to the survivability of American strategic forces. The USSR launched its first successful photoreconnaissance satellite, Zenit 2, in April 1962, initiating a program that would place dozens of film return and later electro-optical surveillance platforms into low Earth orbit. These satellites passed over the continental United States multiple times each day, photographing ICBM fields in Montana and North Dakota, submarine pens in Washington and Connecticut, bomber bases across the Midwest, and command bunkers buried beneath the Rocky Mountains. Soviet mission planners understood that accurate targeting data was the foundation of any first strike scenario, and orbital reconnaissance provided the coordinates, hardness estimates, and deployment patterns necessary to program SS-18 and SS-19 missiles for counterforce strikes against American nuclear assets. The Pentagon's response came in the form of early anti-satellite research programs that explored everything from ground-based interceptor rockets to co-orbital killer satellites equipped with explosives or kinetic projectiles. The U.S. Army and Air Force tested primitive ASAT concepts throughout the 1960s, including the Program 437 Thor missile system stationed at Johnston Atoll in the Pacific, which could theoretically loft a nuclear warhead into space to destroy Soviet satellites with electromagnetic pulse and radiation effects. But these early systems were slow, inaccurate, and required extensive preparation, limiting their utility in a fast-moving crisis where Soviet reconnaissance satellites might pass over critical targets in minutes. What the United States needed was a rapid response weapon capable of reaching orbit quickly, tracking a satellite moving at hypersonic velocity, and destroying it through direct kinetic impact without reliance on nuclear detonation or fragmentation warheads that might damage American satellites in adjacent orbits. The breakthrough came in the late 1970s when Vought Corporation's Aerospace division proposed the ASM-135 ASAT, an air-launched miniature vehicle designed to be carried aloft by an F-15 Eagle fighter and released at high altitude, where its 3-stage solid-fuel rocket motor would accelerate a miniature homing vehicle into the satellite's orbital path. The concept was elegant in its simplicity. The F-15 would climb to approximately 38,000 feet in a steep zoom maneuver, reaching a precise ballistic window where the ASAT missile could be released with sufficient velocity and trajectory to intersect the satellite's orbit. The first stage of the ASM-135 was a modified AGM-69 SRAM rocket motor providing the initial boost, followed by a second-stage Altair III motor that carried the payload above the atmosphere, and finally a third-stage Thiokol Star-27 motor that accelerated the miniature homing vehicle to orbital velocity. The MHV itself was a masterpiece of compact engineering, weighing just 30 pounds and equipped with an infrared seeker that locked onto the satellite's heat signature from the warmth of its electronics and solar panels. Unlike radar-guided interceptors that could be jammed or confused by electronic countermeasures, the MHV's passive infrared sensor simply tracked the target's thermal emissions, requiring no active illumination that might alert Soviet ground controllers. Once the seeker acquired the satellite, 8 small hydrazine-fueled thrusters adjusted the MHV's trajectory with microcorrections, ensuring a direct collision that would destroy the target through pure kinetic energy. At closing speeds exceeding 25,000 miles per hour, the impact released energy equivalent to several pounds of high explosive, sufficient to shatter any satellite into fragments too small to function. Soviet intelligence first learned of the ASM-135 program in 1982, when the U.S. Air Force began captive carry tests with inert missiles mounted beneath F-15 fighters at Vandenberg and Edwards Air Force bases. KGB technical officers initially dismissed the concept as propaganda, arguing that the physics of satellite interception were too complex for an air launch system to solve. Their skepticism was rooted in the USSR's own co-orbital ASAT program, which relied on ground-launched Cyclone rockets that placed maneuverable interceptor satellites into orbit, where they stalked their targets over multiple orbits before detonating fragmentation warheads within lethal radius. The Soviet system worked, having successfully destroyed target satellites in tests during the 1960s and 1970s, but it was slow, expensive, and highly visible, requiring launch preparations that American early warning satellites could detect hours in advance. The idea that an aircraft could simply fly a missile into space and hit a satellite on the first pass seemed impossible, a fantasy born from American overconfidence in technology that had not yet been tested against real orbital targets. This dismissal would prove catastrophic when the Reagan administration accelerated ASAT development as part of a broader strategic modernization program designed to restore American military superiority after a decade of post-Vietnam stagnation. In June 1982, the United States publicly announced its intention to test the ASM-135 against an orbiting satellite, prompting immediate protests from the Soviet Union and calls for an international ban on anti-satellite weapons. Moscow proposed a moratorium on ASAT testing, declaring a unilateral suspension of its own co-orbital intercept trials and demanding that Washington follow suit. The Kremlin's sudden interest in arms control revealed an uncomfortable truth. Soviet planners were beginning to realize that their reconnaissance satellites might be more vulnerable than previously assumed, and that American interceptor technology might actually work. The first live-fire test of the ASM-135 system occurred in January 1984, when a modified F-15A successfully launched the missile during a captive carry flight, demonstrating that the weapon could separate cleanly from the aircraft without damaging the Eagle's airframe or control surfaces. Subsequent tests in 1984 and early 1985 validated the missile's propulsion stages and the MHV's infrared seeker performance, but none of these trials involved an actual satellite intercept. The final test, scheduled for September 1985, would be the proof of concept that the Pentagon needed to justify full-scale production and deployment of an operational ASAT capability. The target chosen for destruction was Solwind P-78-1, a NASA solar observation satellite launched in 1979 to study the Sun's corona and solar wind phenomena. The satellite had been malfunctioning for several years, losing its stabilization and tumbling slowly through space, but it remained in a stable orbit at an altitude ideal for testing the ASM-135's engagement envelope. Selecting Solwind as the target generated controversy within the U.S. government, as NASA scientists protested the loss of a still-functional research platform that continued to transmit valuable data despite its degraded condition. The Air Force overruled these objections, arguing that operational ASAT capability was a strategic necessity that outweighed the scientific value of a single failing satellite. On September 13, 1985, Major Pearson's F-15 took off from Vandenberg and climbed to an altitude of 38,000 feet over the Pacific Ocean, positioning the aircraft on a precise heading that would align the missile's trajectory with Solwind's orbital path. At the designated moment, the ASM-135 released from the centerline pylon, igniting its first stage motor and streaking upward on a column of white exhaust that was visible for hundreds of miles. The second and third stages fired in sequence, propelling the miniature homing vehicle beyond the atmosphere and into the edge of space, where its infrared seeker locked onto Solwin's thermal signature and began its final approach. The intercept occurred at an altitude of 345 miles above the Earth, far beyond the operational ceiling of any aircraft, and well into the region where satellites complete their orbits in the silence of vacuum. Solwin was traveling at approximately 17,000 miles per hour when the MHV struck it head-on at a combined closing velocity exceeding 25,000 miles per hour, releasing kinetic energy that instantly vaporized portions of both objects and shattered the satellite into hundreds of fragments. Ground-based radar tracking stations operated by the U.S. Space Command detected the collision within seconds, observing the sudden multiplication of radar returns as Solwin's coherent structure disintegrated into a debris cloud that would slowly disperse along the satellite's original orbital path. Telemetry from the MHV ceased at the moment of impact, confirming that the interceptor had achieved its mission and destroyed itself in the process. The test was a complete success, demonstrating that the United States could place a kinetic kill vehicle on a collision course with an orbiting satellite using an air-launch system that could be deployed rapidly from multiple airfields worldwide. Soviet radar operators monitoring the test from tracking stations in the Far East watched in disbelief, as American technology accomplished what Kremlin analysts had dismissed as impossible just months earlier. The destruction of Solwin generated 285 catalogued pieces of orbital debris, most of which remained in orbit for years, with the last fragment finally re-entering the atmosphere in May 2004. The debris field became a lasting reminder that kinetic anti-satellite weapons created hazardous environments for all spacecraft, including those belonging to the attacking nation, a fact that would later drive international efforts to ban debris-generating ASAT tests. The immediate strategic impact of the September 1985 test reverberated through Soviet military planning, with a force that surprised even American intelligence analysts. Declassified CIA assessments from 1983 had predicted that Moscow would view the ASM-135 as a significant threat to its low-altitude reconnaissance satellites, particularly the nuclear-powered RORSAT radar ocean surveillance satellites that tracked U.S. Navy carrier battle groups and ballistic missile submarines. These satellites operated in orbits between 200 and 300 miles altitude, well within the engagement envelope of the F-15 launched interceptor, and their nuclear reactors made them exceptionally bright infrared targets that the MHV's seeker could acquire at long range. A September 1983 CIA report titled Soviet Satellite Defense Against the U.S. Miniature Vehicle Anti-Satellite Weapon concluded that Soviet engineers would likely develop countermeasures including decoys, electronic jamming, and signature reduction techniques to protect high-value satellites from American interceptors. The report estimated a moderate likelihood that such defenses would be fielded by the late 1990s, giving Moscow a decade to respond to the ASAT threat. But the successful Solwin intercept accelerated Soviet concerns, forcing the USSR to confront the vulnerability of its entire space-based reconnaissance architecture at a time when the Reagan administration was expanding American strategic modernization across multiple domains. Soviet military theorists understood that the United States did not need to destroy every satellite in orbit to cripple Moscow's intelligence-gathering capability. Eliminating just a few critical reconnaissance platforms during the opening hours of a conflict would leave Soviet commanders blind to American bomber launches, submarine movements, and ICBM dispersals, fundamentally undermining the USSR's ability to execute a coordinated nuclear strike or conventional offensive. The Soviet response to American ASAT capability took multiple forms, beginning with intensified diplomatic efforts to negotiate a comprehensive ban on anti-satellite weapons testing and deployment. In November 1987, the White House and Congress agreed to extend a testing moratorium that had been imposed by legislative action in 1986, effectively halting further live-fire demonstrations of the ASM-135 system. The moratorium was driven partly by arms control concerns and partly by budgetary pressures, as the Air Force struggled to justify the cost of full-scale ASAT deployment when the Reagan administration's Strategic Defense Initiative was absorbing billions of dollars in research funding. Despite the testing ban, the ASM-135 program continued in a reduced capacity, with the Air Force maintaining a small inventory of operational missiles and keeping several F-15 fighters configured for ASAT missions. This residual capability remained classified for several years, with only a handful of pilots and ground crews aware that the United States retained the ability to destroy satellites on short notice if national command authorities ordered such action. The testing moratorium lasted through the late 1980s and early 1990s, a period during which the Soviet Union collapsed and the Cold War ended, fundamentally altering the strategic context that had driven ASAT development in the first place. The ASM-135 program was officially terminated in 1993, with Congress redirecting funding toward other space control technologies, including ground-based lasers and kinetic interceptors, designed for ballistic missile defense rather than satellite destruction. However, the basic architecture that made the ASM-135 successful, air-launched interceptors, infrared seekers, and direct kinetic impact, would resurface in subsequent American ASAT programs and influence the development of similar systems by China, Russia, and India in the decades that followed. The technical legacy of the ASM-135 extended far beyond its brief operational life, establishing design principles and engagement concepts that shaped every subsequent anti-satellite weapon. The miniature homing vehicle pioneered the use of compact infrared seekers for exoatmospheric intercepts, demonstrating that passive sensors could reliably track and engage space targets without active radar illumination. This capability would prove critical in the development of missile defense interceptors, including the exoatmospheric kill vehicle used by the ground-based Midcourse Defense System and the Standard Missile-3 interceptor deployed on U.S. Navy Aegis cruisers and destroyers. Both of these systems rely on infrared seekers that detect the heat signatures of ballistic missile warheads or satellites, guiding kinetic kill vehicles to direct collisions that destroy targets through impact energy alone. The ASM-135 also validated the concept of air-launched space interceptors, showing that fighter aircraft could serve as mobile ASAT launch platforms that were far more flexible and survivable than fixed ground-based systems. An F-15 carrying an ASAT missile could operate from virtually any airfield with sufficient runway length, allowing the United States to position intercept capability near potential conflict zones without the political complications of stationing ground-based missiles on foreign soil. This flexibility was particularly valuable in scenarios where Soviet satellites passed over regions where the United States had limited ground infrastructure, such as the Arctic or the southern Pacific Ocean. The air launch concept also complicated Soviet defensive planning, as Moscow could not predict where ASAT-equipped F-15s might be stationed or when they might be scrambled to intercept passing reconnaissance satellites. The psychological impact of the Solwind intercept on Soviet military leadership cannot be overstated, as the test demolished assumptions about space sanctuary that had governed Soviet strategic planning since the beginning of the space age. For decades, Soviet commanders had treated orbital reconnaissance as a secure intelligence source, confident that satellites operated in an environment where American military power could not reach them. The destruction of Solwind proved that this confidence was misplaced, forcing Soviet planners to develop contingency plans for conducting military operations without satellite support. This shift was particularly destabilizing because Soviet conventional and nuclear doctrine relied heavily on space-based reconnaissance for targeting data, early warning of missile launches, and real-time battlefield intelligence. The loss of these capabilities in the opening hours of a conflict would leave Soviet forces operating with World War II-era situational awareness, dependent on ground-based radar, aircraft reconnaissance, and human intelligence sources that were far slower and more vulnerable than orbital sensors. American strategic planners understood this dependency and began incorporating ASAT strikes into operational concepts for both conventional and nuclear conflict. Declassified U.S. military documents from the mid-1980s describe scenarios in which F-15 launched ASM-135 interceptors would destroy Soviet RORSAT radar satellites and photo reconnaissance platforms within the first minutes of hostilities, blinding Soviet commanders and creating windows of opportunity for American bomber penetrations and submarine-launched missile strikes. These plans assumed that the United States could tolerate the loss of some of its own satellites in exchange for crippling Soviet space-based intelligence, a calculation that reflected the American advantage in alternative reconnaissance methods, including high-altitude aircraft like the U-2 and SR-71, and advanced airborne surveillance platforms that the USSR could not match. The Soviet Union's inability to develop effective countermeasures against the ASM-135 stemmed from fundamental limitations in its space technology and military-industrial capacity. Soviet satellites were generally larger and heavier than their American counterparts, relying on less sophisticated electronics and optics that required more power and generated more waste heat. This made them easier targets for infrared seekers, as their thermal signatures were brighter and more distinctive against the cold background of space. Soviet efforts to reduce satellite infrared signatures through improved thermal insulation and heat rejection systems made only marginal improvements, as the basic physics of satellite design required electronic components to dissipate heat that inevitably radiated into space as detectable infrared energy. Decoy systems that might confuse the MHV seeker were theoretically possible, but they would add weight and complexity to satellites that were already pushing the limits of Soviet launch vehicle capacity. Electronic countermeasures designed to jam or blind infrared sensors were similarly problematic, as they required power supplies and directional antennas that would further increase satellite mass and thermal output. The most effective countermeasure would have been to place high-value reconnaissance satellites in higher orbits beyond the ASM-135's engagement envelope, but this solution brought its own challenges. Higher orbits required more powerful launch vehicles and more fuel for orbital maneuvers, and they reduced the resolution of photo reconnaissance imagery by increasing the distance between the satellite and its targets on Earth. Soviet planners faced an impossible trade-off. Keep reconnaissance satellites in low orbits where they provided the best intelligence but remained vulnerable to American interceptors, or move them to higher orbits where they were safer but less capable. The USSR chose to maintain its low-altitude reconnaissance architecture, accepting the vulnerability as the price of operational effectiveness and betting that diplomatic efforts to ban ASAT weapons would succeed before the United States deployed enough interceptors to threaten Soviet space assets on a large scale. The debris created by the Solwind intercept became a lasting environmental problem that highlighted the strategic and technical drawbacks of kinetic anti-satellite weapons. The 285 fragments cataloged by U.S. Space Command tracking systems ranged in size from small bolts and fasteners to large sections of the satellite's main structure, all of them traveling at orbital velocity in trajectories that intersected the paths of other satellites. Some fragments remained in orbit for nearly 20 years, posing collision hazards to spacecraft from multiple nations including Soviet, American, European, and later Chinese and Indian platforms. The debris field demonstrated that ASAT weapons using direct kinetic impact created indiscriminate hazards that endangered all space users, including the attacking nation, a phenomenon that would later be termed the space debris problem, as the number of satellites and defunct rocket stages in orbit increased throughout the 1990s and 2000s. Each piece of debris represented a potential collision that could destroy or damage an operational satellite, creating even more fragments in a cascading effect known as the Kessler syndrome, named after NASA scientist Donald Kessler, who first described the phenomenon in 1978. Kessler predicted that if debris generation continued unchecked, low Earth orbit could become so cluttered with fragments that collisions would become inevitable, eventually rendering entire orbital regions unusable for satellites or manned spacecraft. The Solwind intercept was an early example of this risk, and it prompted growing international concern about the long-term sustainability of space operations in an environment increasingly threatened by man-made hazards. By the early 2000s, the debris problem had become severe enough that the United States and other spacefaring nations began developing guidelines for responsible space operations, including commitments to avoid creating long-lived debris through kinetic ASAT tests or intentional satellite destructions. The political and strategic ramifications of American ASAT capability extended beyond the immediate military threat to Soviet reconnaissance satellites, influencing broader debates about space weaponization and arms control that continue to this day. The Reagan administration's pursuit of the Strategic Defense Initiative, popularly known as Star Wars, raised fears that the United States was seeking to militarize space on a scale that would destabilize strategic deterrence and trigger a new arms race in orbit. Critics argued that ground-based and space-based missile defense systems would undermine the doctrine of mutually assured destruction by allowing one side to launch a nuclear first strike while defending itself against retaliation. The ASM-135 program fed into these concerns, as it demonstrated that the United States had the technical capability to place weapons in space or launch interceptors from the ground and air to destroy targets in orbit. Soviet propaganda portrayed American ASAT development as an aggressive act that threatened peaceful uses of space and violated the spirit, if not the letter, of the 1967 Outer Space Treaty, which prohibited the placement of nuclear weapons in orbit, but did not explicitly ban conventional space weapons or anti-satellite systems. Moscow used the ASAT issue as leverage in broader arms control negotiations, linking proposals for ASAT test bans to discussions about strategic nuclear weapons limits and intermediate-range missile deployments in Europe. The Reagan administration rejected these linkages, arguing that Soviet co-orbital ASAT systems and anti-ballistic missile defenses around Moscow gave the USSR military advantages in space that the United States needed to counter with its own capabilities. This impasse prevented meaningful progress on space arms control until the end of the Cold War, when both superpowers began reducing their military space programs as part of broader defense budget cuts. The lessons learned from the ASM-135 program influenced subsequent American thinking about space control and the role of anti-satellite weapons in national security strategy. The successful Solwind intercept proved that satellites were vulnerable to kinetic attack, but it also demonstrated that ASAT operations carried significant political, environmental, and strategic risks that limited their utility. The debris generated by a single intercept could endanger dozens of other satellites, including those belonging to the attacking nation or its allies, creating hazards that persisted for years or even decades. The act of destroying a satellite was also inherently escalatory, as it signaled hostile intent and could trigger retaliation in space or other domains, potentially leading to a cascade of satellite destructions that left all parties worse off. These considerations led U.S. space strategists to explore alternative space control methods that could disable or disrupt satellites without creating debris, including electronic jamming, cyber attacks against satellite control systems, and directed energy weapons such as ground-based lasers that could dazzle or damage satellite sensors without physically destroying the spacecraft. These non-kinetic approaches offered the advantage of reversibility, allowing commanders to temporarily blind or degrade an adversary's satellites during a crisis, while preserving the option to restore normal operations if tensions de-escalated. They also avoided the debris problem that made kinetic ASAT weapons increasingly unacceptable in an era of dense orbital traffic and growing commercial space activity. By the 2010s, the United States had developed a diverse portfolio of space control capabilities ranging from cyber operations and electronic warfare to ground-based lasers and maneuverable satellites that could inspect or interfere with other spacecraft, all of them designed to provide options short of physical destruction for managing threats in space. The Chinese anti-satellite test in January 2007, which destroyed a defunct weather satellite at an altitude of more than 500 miles, demonstrated that other nations had absorbed the lessons of the American ASM-135 program and developed their own kinetic ASAT capabilities. The Chinese test used a ground-launched interceptor rather than an air-launched system, but the basic concept was identical. A direct-ascent missile carrying a kinetic kill vehicle that homed on the target's infrared signature and destroyed it through impact energy. The test created more than 3,000 pieces of trackable debris, far more than the Solwind intercept, and the fragments remained in orbits that will persist for decades or even centuries, posing collision hazards to satellites from all nations. The Chinese test shocked the international space community and prompted renewed calls for a ban on debris-generating ASAT weapons, leading to a 2022 commitment by the United States to refrain from direct-ascent ASAT testing as a matter of national policy. This commitment represented a significant shift in American strategy, acknowledging that the long-term sustainability of space operations was more important than demonstrating kinetic intercept capability against satellites. The policy also reflected growing recognition that space had become a congested and contested environment where all nations depended on orbital infrastructure for communications, navigation, weather forecasting, and intelligence, making indiscriminate weapons that endangered all satellites increasingly unacceptable. Other spacefaring nations, including France, Germany, and Japan, endorsed the U.S. commitment and pledged to avoid kinetic ASAT tests, creating the foundation for a new international norm that might eventually be codified in a formal treaty or agreement. The evolution of American anti-satellite strategy from the kinetic interceptors of the 1980s to the diverse space control capabilities of the 2020s reflects a broader maturation in thinking about space as a military domain. The ASM-135 program represented a first-generation approach to space warfare, focused on demonstrating technical feasibility and deterring adversary use of space-based reconnaissance through the threat of satellite destruction. This approach was effective in proving that satellites were vulnerable and forcing the Soviet Union to reconsider its assumptions about space sanctuary. But it also revealed the limitations of kinetic weapons in an increasingly crowded orbital environment where debris creation carried unacceptable risks. Subsequent generations of American space control systems emphasized precision, reversibility, and effects that could be tailored to specific military objectives without creating long-term hazards. Ground-based jammers could disrupt satellite communications without physically damaging the spacecraft, allowing normal operations to resume once the jamming ceased. Cyberattacks could disable satellite control systems or corrupt data streams, achieving similar effects with even less risk of escalation or collateral damage. Directed energy weapons such as high-power lasers could dazzle optical sensors or overheat electronic components, temporarily blinding reconnaissance satellites without destroying them or creating debris. These non-kinetic approaches reflected a more sophisticated understanding of space operations, recognizing that the goal was not to destroy satellites, but to deny adversaries the intelligence and services those satellites provided, a distinction that allowed for more flexible and proportionate responses to threats in orbit. The legacy of the September 1985 Solwind intercept endures in the ongoing debate about space security and the future of orbital warfare. The test demonstrated that determined nations could develop technologies to destroy satellites, ending any illusions about space as a sanctuary immune from conflict. It also showed that such capabilities carried significant costs, both in the debris they created and in the strategic instability they introduced by threatening assets that all nations depended on for critical services. The challenge facing policymakers today is to balance the military utility of space control capabilities against the risks of escalation and environmental degradation that accompany their use. The ASM-135 program proved that satellites could be destroyed, but the more important question is whether they should be, and under what circumstances such extreme measures might be justified. The United States has moved toward a policy framework that treats space as a domain requiring restraint and international cooperation, recognizing that all nations benefit from stable and sustainable orbital operations. This approach does not preclude maintaining defensive capabilities to protect American satellites from attack or developing non-kinetic means to disrupt adversary space systems in conflict, but it does acknowledge that indiscriminate weapons like kinetic interceptors carry risks that outweigh their benefits in most scenarios. The Solwind intercept was a necessary demonstration during the Cold War, a moment when proving American technological capability was essential to deterring Soviet aggression and maintaining strategic stability. But it also served as a cautionary example of what not to do, a reminder that space warfare carries consequences that extend far beyond the immediate military objectives and affect all users of the orbital environment. The technical sophistication required to intercept and destroy a satellite moving at 17,000 miles per hour in the vacuum of space represented a pinnacle of Cold War aerospace engineering, pushing the limits of propulsion, guidance, and sensor technology. The ASM-135's three-stage rocket motor had to accelerate the miniature homing vehicle from subsonic aircraft speeds to orbital velocity in a matter of minutes, achieving precise trajectory control while burning tons of solid propellant in a carefully choreographed sequence. The MHV's infrared seeker had to distinguish the satellite's faint thermal signature from the background clutter of Earth's atmosphere and the cosmic infrared radiation that fills space, a task that required sensitive detectors cooled to cryogenic temperatures and sophisticated signal processing algorithms. The 8 hydrazine thrusters that provided final trajectory adjustments had to fire with millisecond precision to correct for any deviations in the MHV's approach path, ensuring that the interceptor struck its target within a collision envelope measured in feet. Any failure in these systems, a motor that underperformed, a seeker that lost lock, a thruster that misfired, would have resulted in a clean miss and the end of the ASAT program before it truly began. The fact that the Solwind intercept succeeded on the first live-fire attempt against a real orbital target testified to the skill and dedication of the engineers, technicians, and test pilots who developed and validated the ASM-135 system, overcoming countless technical challenges and unknowns in a compressed development schedule driven by strategic urgency. Soviet military analysts who reviewed the Solwind intercept in classified assessments produced for Kremlin leadership struggled to explain how American engineers had solved the guidance and propulsion challenges that had stymied Soviet attempts to develop comparable air-launched ASAT systems. The USSR had experimented with similar concepts in the 1970s, including proposals to launch kinetic interceptors from high-altitude aircraft, but these programs never progressed beyond preliminary studies due to technical obstacles and resource constraints. Soviet aerospace engineers lacked the lightweight materials, miniaturized electronics, and precision manufacturing techniques that made the ASM-135 possible, forcing them to rely on heavier and less capable designs that required larger launch vehicles and longer engagement times. The MiG-31 interceptor, which entered service in the early 1980s, was briefly considered as a platform for an air-launched ASAT missile. But the project was abandoned after calculations showed that even the MiG-31's high speed and altitude performance could not provide the launch conditions necessary for successful satellite intercepts. This technical gap reflected broader disparities between American and Soviet aerospace industries, disparities that became increasingly apparent as the Cold War progressed, and the United States fielded systems like the F-117 stealth fighter, the B-2 bomber, and the GPS satellite navigation network that the USSR could not match. The Solwind intercept was another data point in a pattern that Soviet leaders found deeply troubling. American technology was advancing faster than Soviet industry could respond, creating military advantages that threatened to make the USSR's massive conventional forces and nuclear arsenal irrelevant in a conflict dominated by precision, speed, and information superiority. The strategic implications of American ASAT capability extended to the broader balance of power in the Cold War's final decade, a period marked by economic stagnation in the Soviet Union and accelerating technological innovation in the West. The Reagan administration's military buildup challenged Moscow's ability to compete across multiple domains simultaneously, forcing Soviet planners to allocate scarce resources among strategic nuclear modernization, conventional force improvements, and emerging threats like American cruise missiles and stealth aircraft. The ASM-135 program added space control to this growing list of challenges, requiring the USSR to invest in satellite hardening, countermeasures development, and redundant reconnaissance systems that diverted funding from other priorities. Soviet General Secretary Mikhail Gorbachev recognized that the USSR could not sustain this level of military competition without reforms that improved economic performance and reduced the defense burden on Soviet society. His policies of glasnost and perestroika aimed to revitalize the Soviet system, while negotiating arms control agreements that would slow the pace of American military modernization and reduce tensions with the West. The ASAT issue became entangled in these broader negotiations, with Soviet diplomats proposing comprehensive bans on space weapons as part of larger deals covering strategic nuclear forces, intermediate-range missiles, and conventional arms in Europe. These proposals gained traction in the late 1980s as both superpowers recognized the mutual benefits of constraints on destabilizing technologies, leading to a series of agreements that reduced nuclear arsenals and limited missile deployments. The ASAT testing moratorium agreed to by the United States in 1987 was an early manifestation of this shift toward arms control, reflecting growing recognition that unrestricted competition in space weapons carried risks that neither side could afford. The collapse of the Soviet Union in 1991 fundamentally altered the strategic context that had driven American ASAT development, removing the primary threat that justified maintaining kinetic interceptor capability. The newly independent Russian Federation inherited the USSR's space program, but lacked the resources to maintain the vast reconnaissance satellite network that had supported Soviet military operations during the Cold War. Russian satellite launches declined dramatically in the 1990s as economic crisis and political instability crippled the country's aerospace industry, leaving Moscow with a fraction of the orbital assets it had possessed at the height of Soviet power. This decline reduced the perceived need for American ASAT weapons, as the threat of overwhelming Russian space-based reconnaissance had evaporated along with the Soviet military machine that depended on it, the U.S. Air Force allowed the ASM-135 program to lapse quietly, retiring the last operational missiles and converting the modified F-15A fighters back to standard air-to-air configurations. The pilots and ground crews who had maintained readiness for satellite intercept missions moved on to other assignments, taking with them the institutional knowledge and operational experience that had made the program successful. For nearly 2 decades, anti-satellite warfare receded as a major concern in American defense planning, replaced by more immediate threats like terrorism, regional conflicts, and the proliferation of weapons of mass destruction to rogue states. The resurgence of great power competition in the 2010s, driven by China's rapid military modernization and Russia's reassertion of its strategic interests, brought space control issues back to the forefront of American security policy. China's 2007 ASAT test and subsequent demonstrations of direct-ascent interceptor technology signaled Beijing's determination to challenge American dominance in space, while Russia developed new co-orbital satellites capable of inspecting or interfering with other spacecraft. These developments forced the United States to reconsider its approach to space warfare, leading to the establishment of the U.S. Space Force in 2019 as a separate military branch focused on protecting American interests in orbit. The lessons learned from the ASM-135 program informed this new generation of space control capabilities, but with important modifications that reflected changed circumstances and evolved thinking about space security. Rather than relying primarily on kinetic interceptors, American space strategists emphasized resilience through satellite constellation architectures that could absorb losses and continue operating, electronic warfare capabilities that could disrupt adversary space systems without creating debris, and cybersecurity measures that protected satellite control networks from intrusion or sabotage. These approaches recognized that space had become too important and too crowded for indiscriminate weapons, and that long-term American interests lay in preserving space as a usable domain, rather than turning it into a debris-filled hazard zone that endangered all satellites regardless of ownership. The story of how the United States developed the capability to destroy satellites in orbit demonstrated that capability with the Solwind intercept, and then chose to pursue alternative approaches, reflects a broader evolution in American strategic thinking about technology, deterrence, and the use of force. The ASM-135 program emerged from a specific historical moment when Soviet reconnaissance satellites posed a clear and present threat to American nuclear forces, and when demonstrating technical capability was essential to maintaining credible deterrence. The successful test achieved its immediate objective of proving that satellites were vulnerable and forcing the USSR to reconsider its assumptions about space security. But the test also revealed costs and risks that were not fully appreciated at the time, including the long-term environmental consequences of debris creation and the strategic instability introduced by weapons that threatened all space users. These lessons shaped subsequent American policy, leading to greater emphasis on non-kinetic space control methods and international norms that discourage debris-generating ASAT tests. The balance between maintaining effective military capabilities and preserving the long-term sustainability of space operations remains a central challenge in U.S. space policy, one that requires continuous adaptation as technology advances and new competitors emerge. The ASM-135 program demonstrated that America could destroy satellites if it chose to do so, but the more important question is whether such destruction serves American interests in a world where all nations depend on space for vital services. The answer to that question continues to evolve as policymakers grapple with the complexities of space security in an era of renewed great power competition. The technical and operational legacy of Major Pearson's September 1985 intercept mission extends through every subsequent development in space control technology, from missile defense interceptors to satellite protection systems. The kill chain that linked F-15 launch platform, rocket booster stages, infrared seeker, and kinetic warhead established an engagement model that remains relevant today, even as the specific hardware has evolved. Modern missile defense systems like the ground-based mid-course defense interceptors stationed in Alaska and California use similar concepts, ground-based launchers instead of aircraft, but the same basic approach of accelerating a kill vehicle to intercept velocity, guiding it with infrared sensors, and destroying the target through direct impact. The Standard Missile 3 deployed on U.S. Navy Aegis ships follows an even more direct lineage from the ASM-135, using ship-launched boosters to place kill vehicles on intercept trajectories against ballistic missile warheads in their mid-course phase of flight. These systems benefit from decades of technological advancement since the Solwind test, including more powerful computers, more sensitive infrared detectors, and more precise guidance algorithms, but they employ the same fundamental principles that made the ASM-135 successful. The confidence that American engineers and military planners have in these systems today rests in part on the proof of concept provided by that single test in September 1985, when a 30-pound interceptor traveling at orbital velocity struck a tumbling satellite and validated the physics and engineering that make kinetic intercepts possible. The psychological impact of knowing that satellites can be destroyed continues to shape how nations design, deploy, and operate their orbital assets. Satellite operators today assume that their spacecraft are vulnerable to attack, whether from kinetic interceptors, directed energy weapons, or cyberattacks against ground control stations, and they build redundancy and resilience into their systems to ensure mission continuity even after losses. Commercial satellite operators diversify their constellations across multiple orbital planes and altitudes, ensuring that no single adversary action can eliminate their entire capability. Military satellite programs emphasize hardening against physical and electronic attack, incorporating shielding, encryption, and autonomous operation modes that allow satellites to continue functioning even when ground communications are disrupted. The assumption of vulnerability drives investment in satellite surveillance and tracking systems that monitor all objects in orbit, providing warning of potential threats and enabling evasive maneuvers when necessary. This defensive mindset represents a fundamental shift from the early space age, when satellites were assumed to be safe by virtue of operating beyond the reach of terrestrial weapons. The Solwind intercept shattered that assumption permanently, forcing all space operators to treat orbit as a contested environment where survival depends on active defense and resilient design. The long-term consequence of this shift is a more complex and expensive space architecture, but one that is far more likely to survive and function in contested conditions. The ethical and legal questions raised by anti-satellite weapons remain unresolved in international law, creating ambiguity about when and how nations may use force in space. The Outer Space Treaty of 1967 prohibits placing weapons of mass destruction in orbit, but does not address conventional weapons or anti-satellite systems, leaving a legal gap that nations have exploited to develop ASAT capabilities. Some legal scholars argue that kinetic interceptors violate the treaty's prohibition on harmful interference with other nations' space activities, while others contend that self-defense rights recognized in the United Nations Charter extend to space and justify ASAT weapons as legitimate tools of military power. This legal uncertainty complicates efforts to establish clear norms and rules governing space warfare, as nations disagree about what actions are permissible and under what circumstances. The lack of agreed-upon rules creates risks of miscalculation and escalation, as adversaries may interpret defensive actions as offensive preparations or respond disproportionately to perceived threats. The United States has sought to address these risks through diplomatic engagement and confidence-building measures, including the 2022 commitment to refrain from debris-generating ASAT tests and proposals for voluntary codes of conduct that establish basic norms for responsible space operations. These initiatives aim to create a framework of mutual restraint that reduces the likelihood of conflict in space, while preserving the flexibility to defend vital national interests when necessary. The challenge lies in balancing deterrence requirements with arms control objectives, maintaining credible capabilities to counter adversary threats while avoiding actions that trigger destabilizing arms races or environmental degradation. The story of how adversaries believed satellites were untouchable until America destroyed one in orbit is ultimately a story about the relentless advance of technology and the human capacity to weaponize every domain accessible to military force. Space represented the final frontier, a realm beyond the atmosphere where physics seemed to offer sanctuary from earthbound conflict. The vacuum of space, the absence of air for aircraft propulsion, the enormous velocities required for orbital motion, and the vast distances separating satellites from ground-based weapons all suggested that orbit would remain a peaceful domain reserved for scientific exploration and commercial applications. The Soviet Union believed this illusion, investing billions in reconnaissance satellites that operated with confidence born from assumptions about physical impossibility. Then American engineers, driven by strategic necessity and enabled by aerospace technology that pushed the boundaries of the possible, demonstrated that space was just another battlefield where innovation and determination could overcome apparent obstacles. The Solwind intercept was not the end of this story, but rather a pivotal chapter, a proof of concept that opened new possibilities for space warfare while simultaneously revealing the costs and risks of pursuing those possibilities. The satellites that orbit Earth today continue their silent vigil, watching missile silos and naval bases and troop movements below, providing the intelligence and services that modern militaries depend on to function. But they operate with the knowledge that their existence in orbit is conditional, subject to decisions made by distant commanders who might choose to destroy them if strategic calculations tip toward conflict. This vulnerability, first demonstrated on September 13, 1985, remains the enduring legacy of the ASM-135 program and Major Pearson's historic mission. A reminder that technology eliminates sanctuaries and that no domain, no matter how remote or difficult to access, remains beyond the reach of human conflict when nations decide that their security requires the extension of warfare to new frontiers.